Thank you very much for the warm welcome, and I'm excited to be here to have a talk in front of this huge amount of enthusiastic audiences. Thank you very much for coming to this room. So let's start with, let's start. I'm Yuichiro Tachibana, coming from Japan. Nice to meet you guys. Today, my talk is going to be including just mainly two parts. First is just about explaining about the basics of AST, and the second part I would like to introduce my own case, the problem that I actually encountered and I solved in real world that I hope may inspire you in some way about AST. Okay, let's start with the first part, AST, the basics. What is an AST? And AST is simply an abbreviation standing for abstract syntax tree, and it is a kind of abstract representation of source code, in our case, the Python code, that has a tree-shaped data structure. Given this example, please see this. Here's a very simple Python code that assigns the result of 1 plus 2 to a variable x. And it's representing, its corresponding AST looks like this, and its visual representation I draw is on the right side. You can see that the most top level is the module node because it's tree structure. Here is a single root node that is module in that case, and it has the body attribute that is a list of child node that in our case is a single node of assignment that is that is assigned node, whose target in our case is a single name x node because the assignment target here is x, and assigned value is going to be bin op, meaning binary operator node here, and bin op node has attributes left, right, and operation respectively, and in our case, left is a constant value 1, right is constant value 2, and operator is add, representing this mathematical equation. It's very simple, but what's important and interesting is that every Python code can be represented in the form of tree. That is the concept of AST, abstract syntax tree. And Python provides a built-in module named AST to operate something against AST. Once you import AST module, you can use ast.parse method to get the AST from the arbitrary Python script. Once you pass the Python code as string literal to this method, you can get the AST object as a Python object. That sounds interesting. Then you can check its content by using ast.dump. Then you will see its content of AST like this. And here shows that each node of the AST object are the instances of the node classes defined in the AST module. For example, the most top level is AST.module class instance, for example. The next example here is a very simple, again, Python code like this. A equal 1, x equal a plus 2, then printing the resultant x. And we've seen that before, you can get the AST object by using ast.parse method by passing this script to this method. Then you can get the AST object like this. Then you can compile the AST object into bytecode, although we don't have a closer look into compilation itself in this presentation though. The compiled bytecode can be executed finally by using the built-in exec function. Finally, you can get the expected result like this. At this point, let's consider to add some modification on AST, not the source code itself. For example, what if we replace this add node with mult, meaning multiplication? As we've changed the AST, then the compiled bytecode is going to be changed. Then finally, the final result of the program has been changed without modifying the original source code itself. It's a very dynamic and interesting technique to change your program's behavior without modifying the original source code written in Python. So let's see the next example that shows the, one example of actual implementation of this kind of technique written in Python, actual Python code. Example here include add.py that includes a single line of printing the result of 2 plus 3 plus 4. And if you execute this add.py file with the Python command, as expected, you will get the result 9. That is the result of 2 plus 3 plus 4. Let's consider to create our own custom Python runner, run_python.py, like this. That can be used in this way. Like you can call this Python script as a command with an argument pointing to add.py like this. As you can see, this script runner works very similar way like the normal usual Python command like this. What this script does is very simple. It reads the given file that in this case is add.py and execute its content with a built-in exec function. It's very simple. It's a very trivial example. But at this point, let's consider to add some code to modify the AST read from the source code like this. First, as we've seen in the before, we can get the AST object using ast.parse method. Then we can modify it into a new AST object, then compile it to bytecode, then execute bytecode. As a result, interestingly, the result has been changed because we have modified the AST. Again, what's interesting here is that we could change the behavior of the given program without modifying the source code, just by modifying the AST constructed from the source code. So let's see what's done in this AST modification function named add_to_mul. Here is a implementation of the method. First, I defined add_to_mul transformer. That is a kind of custom node transforming class, extending ast.node_transformer-based class that is provided officially as a built-in from the built-in AST module. And inside this AST transforming function, I used its visit method to get the updated AST. By extending the ast.node_transformer-based class, you can create your own custom node transforming class that walked through the given AST object. And if you define some custom callbacks, in this case, that is visit bin op, this node transformer reaches every node that is of type bin op. You can have any control. You can add any modification onto the node. That is, in this case, I've defined this code, this logic, so that if the reached node has an operator of type add, I would like to replace it with mult, meaning multiplication. This is going to be resulting in replacing all addition to a multiplication. Oh, sorry. All right, this is how you can define your own custom AST transformers. Just a side note, let me introduce another class, ast.nodeVisitor class. That is a base class for defining something like the node transformer, but without modification. Just for the purpose of exploring the AST object. I mean, just to analyze its content. So you can imagine the various types of application based on the knowledge I have been explaining. For example, like you can use AST analysis for code analysis. Like, for example, tools like linter are using AST-based techniques like this. Or even you can do some meta programming that modifies, your own programming's, your program's behavior dynamically at runtime. Be careful, it's a very powerful tool. Please do not overuse it, but it's very useful if its use in appropriate cases. All right, since now, until now, I have been explaining the basics of AST. From now on, I'd like to introduce the problem that I actually encountered and solved somehow or to some extent by using AST techniques. First of all, I'd like to talk about just a bit about Pyodide. Have you ever heard that? Probably no, or someone knows. Pyodide is a very unique type of distribution of Python that is, in another word, Python inside JavaScript. Interestingly, you can see here's a JavaScript code. You don't have to understand it. You just know that this is JavaScript code. And interestingly, from JavaScript, you can execute Python code, passing the Python script as a string literal in JavaScript world, passing to Pyodide API like this. And it actually works as expected. So when I saw this very interesting technology, I thought I could make something interesting based on the existing Python framework. So I started my own project that forked the existing Python-based framework that, in my case, was Streamlit. You don't have to learn it in this case. You don't have to take care of it in the details of these technologies in this presentation, by the way. So I wanted to run the Python-based framework on Pyodide runtime, so that the Python-based jobs, Python-based applications can be executed inside the browser. That sounds fun. Although we will not have a closer look into the details of these Pyodide, Streamlit, STLite, or whatever things in this presentation, but I have talked about these things in PyCon Taiwan 2 years ago, or your Python this year, so please take a look the recorded video if you're interested in. And please forget everything about these things. But the core topic I like to talk about in this presentation is the problem I had when I was working with Pyodide thing. That was interoperability between Python and Pyodide. Basically, Pyodide can execute 99% of Python code, but due to its nature, that is based on web browser or JavaScript runtime or things like that, that is slightly or kind of different from our usual environment where we run Python script. It has some differences. For example, its environment is single-threaded, and there is only single event loop managed by the browser that is already running. So due to these kind of differences, there are some Python features that do not work on Pyodide as expected. That are listed in its official documentation. However, in this presentation, I'd like to focus on the features related to asynchronous something. One troublesome example is asyncio.run. Please see this example. It should be work in Python, and it actually does. But if you run this kind of code, you will get an error from Pyodide runtime because asyncio.run does not work in Pyodide environments. So we have to rewrite the source code to something like this, removing asyncio.run and to await the awaited coroutine or asynchronous function object with a top-level await, which looks a bit weird, but it actually works on Pyodide environment, by the way. Next example is simply time.sleep. Time.sleep doesn't work, precisely didn't work, and it had to be replaced with asyncio.sleep. And asyncio.sleep is a synchronous function, so it also must be awaited at the top level. The disclaimer, Pyodide supports time.sleep actually, due to their effort, too much effort, for so much effort to support it. But at the moment I encountered it, it didn't work. So let me use this a good example of the AST application of AST in this presentation. So we thought that, I didn't want the user of Pyodide, the user of my framework, to rewrite their own source code because they have written very good Python code that should be executed, should be able to be run inside Pyodide, right? So what I thought was just to modify AST as we have seen in the previous course. For example, as we have to replace asyncio.run with the top level weight from left to right, I had to rewrite AST like this into this. This is very simple because the argument passed to asyncio.run was just simply awaited. So I could do this by defining my custom node, custom AST transform function, extending it AST.node transformer like what we have seen in the previous slide. Here, see that I defined a visit call custom callback, which means that when this transformer reaches every node in the given AST that is of type call, and if it is it's async io.run, its argument is going to be awaited, and this await node will be replaced with the original call node. Next example is time.sleep should be replaced with async io.sleep. It's also simple, right? If you reaches time.sleep node, it should be replaced with async io.sleep node with top level await node. This also simply done by defining our own custom AST transformer class, extending AST.node transformer like this. One thing we have to take care of more is that we have to add import statement importing async io module, because there might be, the original Python code might not have importing async io module. So once we put all the work together into one AST transformer class, combining all the custom callbacks into single AST node transformer class, it actually works as expected. You don't have to closer look into the details of this implementation. By the way, by defining your own custom node transformer class, and you write your own Python script run method, finally you can get Python script work inside the Pyodide script, Pyodide runtime. However, there is still something to be cared. For example, in the case of time.sleep, I had coded the target method name time.sleep inside our callback. It matches only time.sleep exactly. So what if it's imported in this form? Or what if it's imported as aliased using as keyword? Or what if it's assigned to a different variable name after importing? It doesn't work, right? And as we've seen, I designed my custom transformer to insert import async IO statement at the very top level. But what if it's used inside a narrower scope, for example, like inside a function? It doesn't work. So to overcome this problem, we have to implement our own name resolution mechanism. Name resolution is just a way to know what the given name exactly refers to. Let's see the example. It's all automatically done by Python when you execute your Python script in normal way. But in our case, we have to done by ourselves statistically at the code transformation, AST transformation stage. The details of the resolution in Python is written in the official document. However, I would like to give a rough explanation of it. The outermost scope is a module that is considered a code block. And function or class is also a code block. And when you import it, the imported object is bound to a name inside this code block. And when it's assigned to some variable, it's also bound to a new name in this scope or code block. The same is done in the inside scope as well. So if you want to know what this weight means, it's going to be resolved to the closest weight assignment here. Then you will see weight is sleep. And this finally be resolved to time.sleep. This resolution mechanism is called as name resolution. I cannot provide all the implementation of the name resolution class because it has 100 lines of code. But if you implement it, the problem is going to be solved. However, there are still more cases. For example, as I have said, async.run should be replaced with a weighted function call. But what if it's inside a function? The outer wrapping function should be converted to be asynchronous function. Then it's going to be also a weight at the top level. It's very cumbersome. So to overcome this problem, you have to create a called graph tracker that tracks which function is called from where. So by defining this kind of thing, this problem can be solved. However, but there's still something. For example, what if name is bound conditionally? This name cannot be resolved. What this weight is actually, or this looks good. It can be simply replaced with asyncio.sleep. But what if there is time.py package that override the imported time package itself? It's very difficult. So in my case, I gave up covering this kind of problem. But seriously, this is very important thing to know. This kind of AST analysis transformation things theoretically can cover everything, but in practice, it is very difficult to cover everything 100%. In practice, it's a trade-off between coverage and effort. So we have to. And such kind of dynamic behavior is particularly hard to analyze statically. So we have to determine the line or surface to which our AST program should support. All right, so this is my actual implementation if you're interested in, although I have not provided actual example of my own AST transformer class because it has more than 100 lines of code. But there is actual implementation here linked to this slide, so please take a look if you're interested in. And if you need to do something like this, using existing library is one option. For example, Asteroid is a good AST analysis library that PyLint is based on, and it provides name resolution capability built in, so it should be useful for practical use. At the very end, sorry, it's already timed out. Let me wrap up my presentation in hurry. AST-based approach can achieve what dynamic approaches can't. For example, transforming the program at syntax level. But also it has some limitations, so we have to consider it as well. And as a real-world problem, I implemented such AST-based thing in my project running inside a Pyodide thing so that you can see the actual implementation of the code if you are interested in. Right, thank you very much. I am Ichiro Tachibana. Yes, and you can find my online identity from this name, WHIPHEX. Thank you very much.
Okay, let's start our Q&A session. And I saw I think like a comment on our Slido. I would like to add replacing code with AST tag. It will be a good tool to fix the compatibility when upgrade Python environment version. Do you have any feedback for him?
Yeah, I think it's really true. Personally, I am not so familiar with that field of technique, but I think there are some tools supporting upgrading Python, right? And they are actually using such, AST-based, whatever static analyzing technique, I think.
Thank you. And any question want to ask you, Tachibana-san? Could you, if you have a question, can you raise your hands? Anyone? Anyone else? Here.
Sorry, I have one question. So, you just mentioned that you cannot use that. You have to change code to use await, right? Instead of async IO in the run, so that can be run on the Pyodide environment. So, but since Pyodide is like providing transforming CPython into WebAssembly, so the Python code can be run on top of that on the web in the web browser. So maybe other people will encounter some problem, right? Not just ST. Like I'm not sure if there's any other solutions, like other people, other open source project. They try to run on the browser, but they encounter some similar problem. How they resolve that?
I think there are many different projects using Pyodide that tries to execute Python code on browser, and they should have similar problem, but they may have different approach to solve it. For example, like a PyScript is a good example, I think. PyScript had, sorry, I don't know the most latest situation about them, but like I think they had a different approach, not AST thing. Like I didn't explain the reason why I choose to use AST in my project in this presentation, but it is due to the architecture design of framework itself, actually. So probably the solution might differ in other projects that may have different restrictions or limitation, things like that. Sorry, this is not clear answer, but like let me discuss with it about details later.
Okay, I see a last question on our Slido. Is it possible to do recursive parsing in AST? Doesn't that eliminate the fail case when target function calls inside another?
Simply, yes, it is possible to, traverse node recursively. This is the, most clearly one good benefit of being tree-shaped structure, right? Is, simply if you traverse the node in tree data structure, it's going to be called a recursive something. But the latter part is, doesn't that eliminate the failure case in target function calls inside another? Well, so sorry, I couldn't get what this point to actually, but yes, answer might be yes.
Okay, I think that's all for this session. Let's give a big hand to our speaker, Yuchiro Tachibana-san again. Thank you.
Thank you.